Welcome to the Deep Dive, the show where we take a stack of dense sources. We're talking research papers, engineering reports, really complex technical analyses, and we just distill them.
Right down to the good stuff.
Exactly. We turn it into the concentrated knowledge you need. It's basically your shortcut to being instantly well-informed on some pretty tricky topics.
And we really try to keep all the fascinating details. We're not just here to give you, bullet points.
Yeah,
we want to give you the story, the context, and those surprising aha moments that really make a difficult subject stick in your brain.
Today, we are undertaking a mission, a deep dive into aerospace engineering. We're looking at a really revolutionary approach to falling from the sky.
Okay, I'm intrigued.
This is all about how engineers are solving one of the oldest and honestly one of the most infuriating problems in logistics and space travel.
Which is what?
How to deliver a payload, anything, from the heavens with absolute pinpoint accuracy.
We are talking about a pretty fundamental design shift then. We're moving away from the million-dollar, meticulously sewn, complex textile things we call conventional parachutes.
Right.
And instead, we're embracing what the researchers are actually calling programmable aerodynamic decelerators.
That's the term. And our mission today is to unpack exactly how this breakthrough, which, and you'll love this, drew its inspiration from an ancient Japanese art form, solves that dreaded drift problem.
Okay.
We're going to get into why conventional parachutes are, well, inherently chaotic, and how a simple piece of laser-cut plastic might just change the trajectory of everything from humanitarian aid drops to landing a rover on Mars.
Let's do it.
So to start, I want you to step into the scene with me. It's high stakes, the adrenaline is pumping, the air is thick with tension.
Okay, I'm there.
You are flying a small C-130 transport plane, and below you is a city block that has been completely cut off.
Cut off how? Is it a natural disaster?
Maybe a massive unexpected flood or perhaps a sudden catastrophic infrastructure failure.
Yeah.
The point is people are stranded.
And the ground forces or the survivors, they're signaling from a designated drop zone, I'm guessing.
Exactly. But crucially, that zone is small.
How small are we talking?
Tiny. Maybe it's a single clear rooftop or a clearing the size of a football field, but it's surrounded by obstacles.
Like what kind of obstacles?
High voltage power lines, tall buildings. Maybe it's even near an active military threat. The landing spot is not forgiving.
So if you miss, it's not just an inconvenience. The supplies are either lost or, worse, you're risking lives just trying to recover them. The stakes are incredibly high.
Incredibly high. And your manifest holds critical supplies.
Hmm.
Think high-value cargo, specialized water filtration systems, urgent anti-venom or antibiotics.
Things you can't just lose.
Exactly. Maybe batteries for communication gear. If this specific cargo is lost, lives are immediately at risk. The margin for error here is not small. It is zero. And this is where the real difficulty starts, right? It's not just about getting the plane overhead.
No, it's about navigating that atmospheric boundary layer.
Okay, what's that?
It's just that messy, chaotic, turbulent air that kicks up near the ground. It's especially bad around tall buildings or over uneven terrain. It's like the air is full of invisible potholes.
Got it. So you make the drop.
You make the drop. The cargo pallet slides out. The traditional parachute system deploys perfectly. You see that massive, iconic mushroom canopy open up, generating enormous drag.
And for a second, it looks like a success.
For a second, yeah. But then the invisible hand of the atmosphere, it just catches it.
The wind shear, the thermal currents.
All of it. The wake created by the buildings, all that chaotic energy starts to just buffet the chute. The canopy immediately begins to pitch and sway violently.
It sounds like the parachute is fighting itself.
It is. And then the inevitable happens.
Yeah.
The drift begins. And this isn't just a gentle wobble,
No.
Over the minutes it takes to descend, that vital cargo, meant for that tiny rooftop, is pushed sideways.
And not just by a few feet.
We're talking not just tens of meters, but sometimes kilometers away. You're just watching in agony as that life-saving package ends up landing like 5 blocks away in a flooded, inaccessible ravine.
Or even worse, it lands in a contested zone, a dangerous area, and now you have to send rescuers into harm's way just to find that critical shipment of medicine.
It completely undermines the entire mission.
The whole supply chain is broken at the last, most critical step.
That is the agony of this process.
Yeah.
The critically important cargo becomes a random lottery winner somewhere in the geography far from where it needs to be.
This whole experience, watching your payload just float away, it highlights the fundamental frustration with parachute tech.
It really does.
And it leads to the obvious, really basic question, why? I mean, why, after decades and decades of aerospace development, can't we just make a parachute fall straight down?
Right.
It seems like the most basic requirement of vertical delivery. Just drop it.
That's the core mystery we're unraveling today. Because the surprising and kind of mind-bending answer is that drifting isn't a design flaw. It's not a malfunction.
Wait, what?
That chaotic sideways motion is actually a necessary condition. It's get this, a design requirement of old-school parachutes.
You're kidding me.
They have to glide sideways in order to work.
Hold on. They have to drift to avoid failing entirely. That sounds like a catastrophic compromise built right into the system.
It is.
It's like designing for inefficiency on purpose.
It is the ultimate engineering trade-off. And understanding why they need to drift leads us directly into the heart of the problem, into the villain of our story.
And what's the villain's name?
The villain in our deep dive is known as the stability paradox.
The stability paradox.
It defines this frustrating design choice that's inherent in conventional parachute engineering. The primary job of a parachute is super simple, right? Generate maximum drag to slow down a massive payload.
And to do that, you need a big surface area. You need that big, beautiful, contiguous fabric canopy, the classic mushroom shape.
Exactly. You use a massive, seamless piece of fabric. But here is the paradox. That huge surface area, by stopping the air dead in its tracks, it generates massive, chaotic instability directly behind it.
So it's not just a little air wake.
No, not at all. If we were to use the technical term, what we're actually seeing is something called complex vortex shedding and highly unsteady wakes.
Okay, whoa. Vortex shedding. Unsteady wakes. You have to explain that to me like I'm 7.
Okay. Imagine you're holding a giant umbrella in a really strong wind.
Right.
The wind hits the umbrella and has to go around it. But it doesn't just flow smoothly. It tumbles and swirls off the edges, creating these big, messy whirlpools of air behind you.
And those whirlpools are trying to rip the umbrella out of my hands.
Precisely. Those are the vortices. Now imagine that on the scale of a parachute. You have these immense, swirling, low-pressure zones, giant, unstable air monsters that are constantly trying to pull the parachute apart or flip it or make the canopy just collapse in on itself.
So the very design feature, that large, solid, drag-generating surface, is what creates the chaotic instability that the system then has to try and fix?
Yes.
It's self-sabotage by physics.
It is self-sabotage by physics. That is the perfect way to put it. That self-generated chaos, the intense turbulence, the pitching and swaying that risks a catastrophic canopy failure, that is the single biggest risk during descent.
So you have to stop that instability somehow.
You have to. So how do conventional parachutes fight this monster that they've created?
How?
They deliberately break the symmetry of the airflow. They introduce a small, controlled gliding angle.
Okay, unpack that gliding action for me again. Why does moving sideways solve the stability problem? It feels like it would make it worse.
It seems counterintuitive, right? But think of it like this. When you have perfectly symmetrical flow over the top of the chute, any tiny disturbance, a small gust of wind, a pocket of turbulent air, can flip the parachute completely.
Because the forces are balanced, but unstable, like trying to balance a pencil on its tip.
Perfect analogy. But by initiating a slight forward glide, the parachute is always meeting the air at an angle. It's constantly leaning into the airflow.
Like a boat constantly leaning into the waves to stay upright.
Yes, or a kite. A kite only flies because it's at an angle to the wind. That slight angle on the parachute creates a constant minor sideways force that provides temporary stabilization against all those perturbations and turbulent bumps in the air.
So it's a mechanism of survival. The parachute must glide to keep its canopy inflated and stable enough to even function.
And there it is, the paradox.
Right. Gliding saves the parachute from collapsing, ensuring its structural stability.
But the high cost of that survival is trajectory predictability.
It means the destination is always going to be uncertain. It's pretty much guaranteed to be kilometers away from the target you are aiming for.
It is the unavoidable trade-off. They're designed to survive the fall, not to target the landing zone.
And this trade-off is why, when you look at how traditional systems are actually built, you realize the immense logistical and industrial challenge they present.
That's a crucial point. We're not just talking about a simple sheet. We're talking about highly complex, incredibly expensive textile systems whose complexity is driven almost entirely by the need to manage that self-generated chaos.
It's all just to ensure the structure doesn't destroy itself on the way down.
Let's pull back the curtain on this complexity. Let's use one of the most rigorously tested examples we have. the NASA Orion Capsule Parachute Assembly System.
Okay, so this is the system designed to bring astronauts home safely. The engineering has to be exquisite, but I'm guessing incredibly complicated.
Immensely complicated. We're talking about multiple types of parachutes for a single landing. There are forward bay cover parachutes, or FBCPs. There are drogues. There are pilots. And then two massive mains.
And they're all made of specialized materials like Kevlar and nylon and require this precision rigging.
Oh, the rigging is insane. The sheer quantity of suspension lines for just the main chutes is staggering.
I remember reading the estimate. It's something like 10 miles of specialized, high-strength textile lines.
10 miles, all integrated and sewn together. The manufacturing is inherently delicate and just unbelievably time-consuming.
And the packing process itself is an art form, right? It's not just shoving fabric in a bag.
Not at all. Some components are hand-packed piece by piece. Others require extreme pressure packing to densities that sometimes exceed 40 pounds per cubic foot.
Wow.
And this is all just to ensure a gradual, controlled deployment that manages the huge deceleration forces so it doesn't just rip apart.
And the mechanism they use to manage that deployment chaos, the gradual opening, is where we see this, like, catastrophic complexity. You're talking about reefing systems.
Exactly. To prevent the canopy from just snapping open too fast and tearing itself to shreds, they use reefing loops and bypass loops.
And these are just textile components.
Yeah, they're designed to momentarily restrict the canopy's diameter so that it inflates slowly in stages to manage the load.
But the documents, the source materials, they highlight that even these small, critical components are constant points of failure.
Constant. The initial design actually used metallic reefing rings. They abandoned that pretty quickly because the metal rings themselves were damaging the delicate fabric during deployment.
So they switched to textile reefing loops.
Right. But even there, they ran into these incredible, really counterintuitive failure modes. Specifically in the drogue parachutes, which are the smaller ones that manage the initial heavy loads at high speed.
Okay, what happened?
The textile bypass loops, which route the reefing line around a cutter, they started failing due to abrasion and sawing.
Sawing. The fabric is cutting itself because of the chaotic motion. That detail is shocking.
It is genuinely shocking. Imagine the scenario. The drop is so violently unstable, remember that self-generated chaos we talked about, that the textile components are essentially vibrating against each other at high frequency.
Like a power tool.
It's just like that. When the initial cotton retention ties failed, the reefing line migrated to the sharp corners of the bypass loop, and due to the intense, chaotic motion of the drop, it physically sawed through the fibers.
That paints such a vivid picture of the sheer destructive forces at play. We think of textiles as flexible and resilient, but under this kind of turbulent, high-G movement, they are vulnerable to self-destruction.
And the validation needed just to ensure the safety margins for these complex sewn systems is astounding. To calculate what they call joint efficiency.
Which is the reduction in strength when you sew two pieces of fabric together.
Exactly. Yes, I had to conduct 92 different joint tests.
92.
That required 920 total pulls on a machine, just to confirm the minimum strength of the stitches.
That's a massive, expensive, time-consuming effort simply to understand the limitations introduced by sewing.
And they found unexpected weaknesses even in simple additions, like adding a simple bag stitch to a knot, which was intended to prevent it from unraveling, actually reduced the joint strength more than they predicted.
So it almost wiped out the entire safety margin.
Almost did. Every tiny component, every decision about material, every single stitch introduces new potential points of failure and requires exhaustive, expensive testing.
So to summarize the villain here, traditional parachute design is just this deep well of industrial complexity, high manufacturing costs, a constant threat of textile failure, and an inherent stability paradox that guarantees inaccuracy.
It truly is an engineering bottleneck.
Which I guess proves one thing.
What's that?
You can't solve the problem of chaos by adding more complexity.
You have to change the fundamental way the air interacts with the decelerator.
Yeah.
We needed to look outside the rigid world of textile engineering for a solution.
Okay, so where did they look?
So engineers hit a wall. They needed a decelerator that was simple, stable, and accurate. And the breakthrough, it didn't come from better sewing machines or stronger Kevlar.
Where did it come from?
It came from looking away from heavy textiles and instead toward the elegant, passive art of Japanese paper cutting.
This is where we introduce Kirigami. It's the ultimate pivot, right? From the brutal forces of the atmosphere to something so delicate and precise.
That's right. And Kirigami is often confused with origami, But the distinction is absolutely critical.
Origami is just folding.
Purely folding. Kirigami is the Japanese art of cutting flat sheets. And the genius that the researchers recognized is that these cuts and the deformation that happens after, they're not random.
Okay.
They are used to induce specific, predictable mechanical and dynamic behaviors.
It sounds like they're turning the material from just a passive canvas into an active instruction set.
That is the perfect phrase for it. They are programming a sheet to deform. So instead of spending 10 years designing a complex textile assembly, the researchers, mostly from Polytechnique Montreal and École Polytechnique in France, they started with something deceptively simple.
What was it?
A thin, flexible, solid circular disc, often made of mylar, that tough, light polyester plastic film.
A single plastic disc, replacing miles of specialized textile lines and thousands of hours of rigging. The simplicity is already breathtaking.
And here's the technological innovation. They use a precision laser cutter to introduce a very specific geometric pattern. It's a closed-loop Kirigami pattern of slits into this flat disc.
And those slits are the operating code.
Yeah, the code. This pattern does two things at the same time. It introduces intentional flexibility into the sheet, and, maybe more importantly, it creates controlled porosity.
Engineered holes.
Engineer holes, exactly.
So the cuts aren't random, they are structural instructions embedded right into the material. But what makes that specific closed-loop pattern so effective?
That specific geometry ensures that when the material stretches under the load of the air, the newly formed holes expand in a predictable, stable way.
Okay.
When the structure is released, the air rushes past, and the sheet is forced to deform into a three-dimensional, stably falling shape.
But how does a flat sheet know what shape to take? I mean, when I drop a piece of paper, it just flutters chaotically to the ground. This is the moment where we need the analogy engine.
Okay, yes. This is all about fluid structure interaction, or
Yes.
FSI.
FSI.
It's the dynamic process where a fluid flow, in this case the air, meets a flexible structure, the mylar sheet, and they constantly influence each other.
Okay, FSI. Give me the daily life analogy. Make it stick for me.
All right, think of a cheap, thin plastic grocery bag. If you just drag it behind you while you're running, it flails around chaotically, right?
Totally. It's all over the place.
Now imagine putting pre-cut slots in that bag. That's our Kirigami design.
Yeah.
When you run, the air rushes through those slots. And instead of flailing, the bag puffs up into a stable, predetermined shape. The researchers describe the resulting form as being like an inverted bell or an elegant latticework phase.
Oh, that makes perfect sense. The air pressure isn't just a general chaotic force hitting a solid wall anymore.
Right.
It's interacting with 100 small engineered surfaces that guide the overall structural integrity of the whole thing.
Exactly. And the deformation isn't fixed on the ground. It's a dynamic, moment-by-moment response to the aerodynamic load during the fall. The geometry dictates how the sheet's own elasticity balances the fluid pressure, maintaining what they term a quasi-axisymmetric deformation.
Okay, let's pause on that jargon for the listener. Quasi-axisymmetric deformation. If I were 7, how would you explain that stable shape?
You would say, it means the parachute shape is almost perfectly round, like a vase or a bell, and the pressure is distributed evenly all the way around, keeping it centered.
The key word there is quasi, almost.
Almost. Because the deformation is constantly adjusting slightly, but the overall shape remains stable and centered on the axis of descent. It's continuously and actively maintained by the physics of the air rushing through the programmed cuts.
It's the ultimate contrast to the conventional canopy, which is a passive, rigid structure that creates its own chaos.
Right.
The Kirigami sheet is an active structure that leverages the air pressure for its own stability.
And this wasn't just a lucky guess, a happy accident in the lab. This required serious, fundamental research rigor.
Yeah.
Because the parachute relies on this dynamic morphing under load, a changing shape in a moving fluid standard. Computer simulations were just useless.
Right, you couldn't use the rigid body models they use for planes and missiles. The shape is constantly changing.
No, it's a moving target. They needed a completely custom computational framework, a sophisticated flow-induced reconfiguration model.
And that model had to predict what exactly?
It had to predict exactly how the material, with its specific elasticity and its specific cut pattern, would distort under every imaginable aerodynamic loading scenario. This level of initial research complexity is what allowed them to guarantee the simplicity and reliability of the final product.
So they perfected the code before they even cut the final piece of plastic. That's smart engineering.
And the verification was intense. This project, which had significant funding from groups like the Natural Sciences and Engineering Research Council of Canada, it involved a rigorous hybrid approach.
What do you mean by hybrid?
They used numerical simulations, they did controlled wind tunnel tests in labs, and eventually they did successful outdoor drone deployments.
They tested different sizes.
Oh yeah, they tested prototypes from the size of a dinner plate up to a full meter across. They were proving the concept across massive scale changes.
And this confirms that the simple idea of just cutting a sheet of plastic is grounded in some really rigorous, high-level computational fluid dynamics.
It's an elegant solution built on some very deep science.
Okay, so let's get to the discovery itself.
We've established the chaos of the conventional parachute, right?
Right.
One huge solid surface generating one massive, screaming, turbulent wake behind it.
Right. The air monster.
The air monster. Now let's look at the Kirigami deployment. This is the moment the magic of the cuts takes hold.
If the problem with the conventional design is that it blocks the air too cleanly, creating that unstable, low-pressure zone, what does the Kirigami design do differently?
It doesn't block the air, it programs the air.
It programs the air. I like that.
As the air hits the structure, the tension causes the hundreds of little slits to stretch open. So instead of one single massive disturbance, the air is forced to pass through these tiny engineered openings.
Okay.
And the result is that the air exits the structure in an, and this is a quote, orderly manner without any major chaotic turbulence.
That is the ultimate finding. It's basically pacifying the air.
Yes.
It's giving the air a pre-approved, programmed exit route through the chute, which eliminates the massive vortex shedding that causes all the instability.
Exactly. They suppressed the primary source of instability that plagues all those textile designs.
And this is the critical connection then.
This is it. Because the air is behaving,
Yeah.
the parachute no longer needs to generate that stabilizing sideways glide. It eliminates the need for the stability paradox compromise entirely.
So we can finally talk about a trajectory that is ballistic and predictable.
Finally.
What are the metrics on this predictability? I mean, how accurate are we really talking here?
This is where the results are just astonishing. The trajectory is a predictable ballistic descent. Researchers rigorously validated this design's independence from how it was deployed.
Okay.
They confirmed that the Kirigami parachute, and I'm quoting again, always falls near the target, regardless of their initial release angle.
Wait, I need to be skeptical here because that is a fundamental claim that challenges decades of aerospace knowledge.
I know.
If I take a conventional parachute and I drop it sideways, it's going to glide sideways and it's going to land who knows where. How did they test the self-correction?
They tested it dramatically. In controlled indoor lab tests, they specifically launched the Kirigami sheets at varying angles.
Like what?
0 degrees, so straight down, 45 degrees, and even a full 90 degrees, so completely horizontal.
The horizontal launch? A normal parachute would just fly away.
It would just glide off. The Kirigami parachute every single time performed a rapid self-centering action.
Self-centering.
Yeah, it corrected its own attitude, its own angle, and just settled immediately into its stable vertical descent path.
That self-centering effect is the true game changer for accuracy.
It is.
It means that even if the cargo tumbles or is released haphazardly from a drone or a plane, the geometry immediately takes over, recenters the mass, and locks it onto a stable vertical descent.
That's the power of programmed geometry. And this reliability and accuracy, it holds even within those messy, unstable atmospheric boundary layers near the ground.
Because the flow is orderly.
The orderly flow means that external turbulence is just less likely to push the whole chute off axis.
Okay, so what about the payload capability? If it's designed to be so simple, can it still slow down a real load?
They back this up with hard data in the field. During their outdoor drone deployments, they dropped a 1-kilogram water bottle.
Which is a significant payload for a small prototype.
It is. They dropped it from a drone hovering at 60 meters. Now, a free-falling water bottle would be screaming toward the Earth at about 34 meters per second.
And with the chute.
The 0.5-meter Kirigami chute limited the terminal descent speed to a very manageable 14 meters per second.
So it maintains a comparable deceleration capability, at least for these low to medium loads, but with vastly superior control and accuracy. And the landing.
The landing was pinpoint. The chute delivered its payload safely to the ground, quote, directly above its target.
Wow.
The system is robust enough to handle the payload stabilization and descent rate management, all while maintaining that critical self-correction.
Let's talk about the contrast with complexity again. We spent a lot of time detailing the failure points in the Orion system, that endless joint testing, the abrasion, the sawing of the textiles.
Right.
How does the Kirigami design stack up logistically?
It's industrial simplicity versus industrial complexity.
Eh.
The fabrication shifts entirely.
How so?
Traditional parachutes require specialized textile engineering, complex sewing of panels, intricate rigging, specialized handling. The Kirigami method requires one thing.
A single laser-cut plastic sheet.
That's it. Mylar, paper, even cardboard, whatever suits the environment or the mission.
A single monolithic component with one attachment point. That drastically reduces manufacturing costs, time, and, importantly, potential failure points.
No abrasion?
No sawing.
No, not failure.
None of it.
Yeah.
And the design is easily fabricated, and, crucially, it's compatible with high-speed industrial processes like die-cutting presses.
Oh, that's a big deal. Think about that shift. Production goes from a specialized, delicate sewing shop that requires highly trained personnel to a rapid, inexpensive industrial stamping process. It's like stamping out cookie cutters.
That viability for low-cost, high-volume production fundamentally changes the logistics of something like humanitarian aid. You could potentially set up decentralized fabrication in operational areas with minimal training.
Its simplicity as the ultimate form of sophisticated engineering. The inherent reliability and low cost make it scalable not just in size, but globally in terms of accessibility.
Okay, so let's zoom out.
We've confirmed that the Kirigami parachute solves the stability paradox with, elegance and simplicity. Now let's project this discovery onto the real world. What is the immediate impact?
Well, the immediate, most compelling application has to be logistics and humanitarian aid.
For sure.
When you can guarantee that critical supplies land directly in a small, constrained disaster zone, you limit material losses, which can be immense in rough terrain, and you eliminate the need for dangerous retrieval missions.
Imagine a drone delivering antitoxins directly to a specific rooftop in a tightly constrained urban area, regardless of the wind conditions 60 meters up.
It drastically improves the integrity of the supply chain.
Whether we're talking about military logistics, disaster relief, or high-value commercial drone delivery.
And it's cheaper, it's simpler, and it's inherently more reliable because its monolithic nature eliminates all those complex points of failure associated with lines and textile joints.
Now, let's go further afield literally. The predictable vertical descent capability is absolutely vital for long-term strategies in planetary exploration.
You're talking about entry, descent, and landing systems. EDL.
Exactly.
This means Mars. The Martian atmosphere is thin, it's tenuous, and it's highly unpredictable.
Right.
Any conventional system deployed there risks massive, unavoidable drift. You could steer a multi-billion-dollar rover kilometers off course, maybe into an unrecoverable crater.
And the Kirigami design offers proactive, geometrically programmed stabilization.
What does that mean?
It means engineers can design a specific cut pattern that is precisely tuned for the thin, low-density atmospheric profile of Mars. This offers an unprecedented level of trajectory control during that final critical descent phase. It's far superior to just passive gliding stabilization.
That sounds like an instant advantage for NASA and other space agencies. You get stability without sacrificing accuracy. But we have to address the biggest current limitation that the sources highlight: the scaling constraint for heavy payloads.
The elephant in the atmosphere.
Yeah.
Because the Kirigami sheet is porous, it's full of holes by design, it inherently produces less drag than a solid sheet of the same diameter.
So if you wanted to drop, say, a human being or a very heavy multi-ton payload, what are we talking about in terms of size?
The estimates are daunting. Scaling this up for a human payload would require a parachute with a radius of approximately 100 meters.
100 meters. That is nearly the entire length of a football field.
It is. And trying to pack and deploy a sheet of plastic that size becomes the logistical barrier that rivals the complexity of the conventional chutes we were criticizing earlier.
That suggests the technology is currently optimized for and best applied to low to medium loads,
Right.
where that simplicity and accuracy trump the need for massive drag generation.
That's the current constraint. But the researchers are not slowing down. They are actively pursuing a comprehensive roadmap to both solve the scaling issue and enhance the functionality.
How do you enhance functionality beyond just falling straight down?
They're exploring patterns that can achieve more complex, programmed behaviors. For instance, programming the sheet for a controlled, deliberate whirling or rotating motion during descent.
Wait, why would you introduce rotation if the goal is absolute stability? That seems like a step backward.
It would integrate perfectly with scientific missions. If the parachute is designed to spin at a controlled, predictable rate, an integrated camera or sensor array could actively scan the surrounding environment as the payload approaches the ground.
Oh, I see. A rover could take a 360-degree topographical panorama of its landing site before it even touches down.
Exactly. It would allow mission control to identify the safest path before the wheels ever hit the dirt.
Okay, that is leveraging the descent time for advanced data gathering. That justifies adding a slight layer of programmed complexity. I get it.
They're also looking at structural hybridization, so
Why?
integrating traditional origami, the folding techniques, with the Kirigami cutting structure.
And that would do what?
Drastically improve packability, which could help with the logistical barrier of that 100-meter sheet.
But the true pinnacle, the ultimate technological leap, has to be overcoming the fixed drag trade-off. To make it viable for the heaviest payloads, you can't have a fixed amount of porosity.
Precisely. And the goal there is active control. This is the most complex, forward-looking objective on their roadmap.
Okay, what does that look like?
It involves covering those intrinsic slits, the programmed holes, with a soft, stretchy film. Then they would use external mechanisms, maybe tiny actuators, to modulate the exposed porosity in flight.
So you could dynamically open and close the cuts, depending on what the parachute encounters in the atmosphere.
Exactly. You could adjust the drag coefficient in real time. Imagine hitting unexpected, heavy turbulence.
Right.
You could instantly reduce the porosity by stretching the film over the holes, making the surface less porous, and increasing drag to slow down rapidly.
And if you wanted to increase speed or enhance stability in very still air, you could open the slits wider.
Now you're thinking with Kirigami.
That transforms it from a beautifully programmed passive sheet into an intelligent, responsive, semi-active flight system. It's no longer just a decelerator, it's an aerodynamic control surface.
It is.
That's a massive technological jump into the future of flight control.
It fundamentally changes what a parachute is capable of. It successfully resolves two previously competing goals, high stability and exceptional precision, all achieved through simple, brilliant geometric programming.
And that, for me, that's the most profound takeaway about how knowledge advances. You know, they moved past the expensive, high-risk, multi-component engineering solution, and they looked to an ancient, seemingly passive art form.
Yeah.
By translating that elegant interplay of cuts and geometry from Kirigami into active, functional engineering principles, they completely redefined the constraints of aerodynamic deceleration.
Which leaves us with a final thought for you to explore. If engineers can dynamically control the airflow passing through a simple plastic sheet, tuning its drag and its descent rate mid-flight with just a geometric pattern,
Right.
what other seemingly passive or simple materials are just waiting to be programmed using geometry and art? What other everyday flat surface could be given active functional properties and fundamentally change how we move through the world?
That is something to think about.
That's something for you to mull on until the next deep dive.